Here in this video, I would like to demonstrate how a neural network learns and try to imagine a few exciting applications and problems that could be solved with this technique. Here we are going to show small-sized play neural networks to show, in a visual way, how it learns, then what it can do with this knowledge. The problems are voluntarily really simplified for that purpose. In our first play situation, we are going to teach the machine to diagnose diseases depending on symptoms. We will have 17 different symptoms in blue and causes, and 9 possible diagnoses in red. Our pretend diseases are inspired from the real ones. This data has mostly been collected from the pasteur.com website. Many elements in the symptoms area are environmental factors for possible disease and causes. You can see on the right the network in its pre-trained state. To keep this fun and visual, we will train the network with just a few cases elements and then test it with a few lists of symptoms a patient may have, while omitting some, to see how our pretend doctor reacts. We enter training phase. You can see the neural connections being progressively trained in the image on the right. The inputs on the left are the symptoms. The outputs on the right are the possible diagnosis. In the middle is the hidden layer. The green flickering on the outputs indicates that the neural network got a good answer. It will progressively get more and more. Notice that some connections between the neurons are turning darker. As in a biological neural network, during the learning process some connections are becoming stronger and others progressively weaker. It is about to end its training. It is now time to ask it questions. Like a patient will do with his doctor in a consultation, let's feed the predictive model with a list of symptoms and see what diseases it suspects it may be. First case. An elder person says he has joint pain. The model suspects arthritis. Next case. A patient indicates that he feels unwell and suspects that it may be caused by the fact that he hates peanuts. He does not know if he is allergic. The network suspects, among other things, allergies, but it is insufficient and we request from the patient another symptom. The patient then also indicates that his throat has been swelling. The second symptom leaves no doubt to the predictive model. It is probably an allergy. Next, this patient indicates a fever and a runny nose. The network suspects a common bronchitis. Another patient also indicates that he has fever and that he recently traveled in a tropical area. The network diagnoses a bronchitis but also suspects a dengue case, a disease common amongst travelers from those areas. Then, this other patient indicates contact with dust and skin rash. This is probably an allergy. The classification model is limited by the lack of symptoms, diagnosis and training cases, but neural networks are known to adapt well to scalability issues. Now let's try to work on a completely different problem where neural networks can be put to use. Have you noticed how language translators aren't very efficient and often misses the point? There are many factors that make it so hard for a simple program to translate something as complex as a human language. What is meant is not always what is said, and every word may have many meanings depending on the context. Without the ability to get the context, the translation software cannot properly choose the appropriate meaning to a particular word that have multiple homonyms. I would like to demonstrate how to train a neural network to be able to understand the meaning of a word depending on its context. In a professional context, Natural language processing specialists will collect all the words of a given language and try to train all possible meanings. But again, I am going to work on a very simple and visual version of the problem. Let's take a word in the English language, hey. Let's say net. The word net have numerous meanings, but we will focus on 5 of them that have a clear difference between each other. 1. A piece of mesh fabric designed to serve a specific purpose. 2. Any network of reticulate system. 3. Same as previous, but intended virtual. 4. Verb, to catch or ensnare. 5. Verb, to score a point. When we humans hear the word net in a sentence, we are able to deduce the meaning based on the context. To keep the problem simple and visual, we will train the neural network on only a few sentences with different contexts. We are going to keep the keywords, those meaningful to the context, here shown in blue. Our classification model will deduce, when trained, in what context the word net is used, depending on the keyword used. Of course, to get an efficient result, it should be trained with thousands of sentences. But using this simplified example will allow us to notice a few interesting things, as you are about to see. You can see on the left the extracted keywords in blue from the sentences we used to train, used as inputs. To increase efficiency, you are supposed to train data in a random order, but here I injected those sentences in the same order as the output. Notice on the right the neurons turning green in a 1, 2, 3, 4, 5, 6 pattern. This shows us that the neural net started recognizing all the training cases. As in the previous examples, you can notice some connections getting stronger and others getting weaker. Now that it trained on these few cases, let's see what happened when fed with new test sentences. Will it be able to guess the context? First case. I watched the news on the net on my computer. After injecting it with the keyword from our test sentence in blue, the neural network identified the context successfully. The word net here meant as internet. Second case. The man recovered the net and dragged it in the boat. The words between parentheses are being ignored, as this neural network cannot dynamically learn new words, and we must keep its shape for visual purposes. Here, the word boat helps successfully identify the good context. Now let's try something more interesting. I will use now an ambiguous phrase. The police netted a big fish last week. This sentence is synonym of the police caught a big fish, or the police caught a criminal. Even being only trained on so few sentences and as much catch a criminal cases as fishing net cases, it identifies the good context successfully, despite the ambiguous use of fish. In a professional context, the neural network will be of dynamic size and will include all possible words, will be trained on way more test sentences and recognize synonyms. Right now, it is in the same position as a young child that learns to speak, not always being able to distinguish successfully the good context, because of not having been exposed to enough situations where it hears the word. The neural networks, supposing they are built with a design allowing scalability and allowing an efficient learning process, usually become better at a task the more they are fed various training data.